about the Earth stopped getting greener 20 years ago. So this is kind of interesting. Well, something very interesting, actually, because climate change has all kinds of impacts, and some of them have like positive impacts, actually, and then some have negative impacts. One of the theoretically positive impacts of climate change is that when you increase CO2, CO2 is what a lot of climate deniers like to say is plant food. And in a sense, it is. So all life on Earth that you see in front of you is created by CO2, mostly from the atmosphere. So even though CO2 is only 0.04% of the atmosphere, all the trees, all the people, all the cows, all the tigers and insects you see were built out of that carbon that came from the 0.04% of the atmosphere, which is still a lot. It's 3 trillion tons of CO2 in the atmosphere at any one time. So that's quite a bit. But that's one of the positive things, is that when you increase CO2, this is actually one of the feedbacks. When we put a ton of CO2 in the air, roughly speaking, only half remains in the atmosphere because the oceans take up a lot, soils take up a lot, and plants take up a lot. So you increase CO2, more plants grow, and therefore you get, in a sense, more carbon capture from the biosphere. And that means the remaining part of the CO2 that's in the atmosphere is only, I think it's 55%, but it's roughly half of what you put up. And that's really good, because otherwise the CO2 would be twice as much as it is now, and global warming would be much worse. So that's the good news. However, this new research is saying that in addition to CO2 helping plants grow, something else happens. And that is vapor pressure deficit increases. And when that increases, plants don't grow as well. And so what they're saying is that while the greening, the amount of plant growth globally, on average, globally, was going up in the 80s and the 90s, but for the last 20 years, it's been going down. And the reason it's been going down is because of we'll talk about what this is, but the vapor pressure deficit has been increasing. And therefore, that's been overwhelming the CO2 effect that helps plants grow more. And this is pretty serious stuff on a number of levels. Are all, plants not growing as well hurts the ecology in all different ways, agriculture, but forests, are drying out and therefore more prone to forest fires. And also more CO2 ends up in the atmosphere because less is being captured by the plants. So lots and lots of things are going on. So I'm going to read, first of all, yeah.
How do they measure this? How do they measure how much plant growth there is?
Yeah. They measure it by satellites. So satellites, there's certain satellites like the one I worked on 40 years ago called Landsat. And Landsat has different spectral bands or different colors it can record, basically, different frequencies. And you can actually map out green plant. You can see green plants, basically, from space, because they're a combination, certain spectral bands. And since it's taking the whole Earth every once in a while, you get the whole Earth covered. You can run this and basically map out how much green growth there is on Earth.
So what is the comparison? We're comparing now to
about 20 years ago. Yeah.
Okay. And then
or to 10 years ago, to some baseline amount, which was increasing over time. So I think all of this started about 1979 is when we had enough satellite coverage to start recording, land ice and, whatever. The Landsat satellites basically started making full pictures of the Earth every few weeks, basically. Okay. Now they can do it every day. Different satellites do it every day. But back then, so we had references back to 1979. And so we could take a look there. We can see how much green plant growth there was as a baseline and see that over the 80s and 90s that it was increasing. And it was increasing because the temperature hadn't gone up a lot yet, because that's what affects the vapor pressure deficit. But that didn't go up much, but the CO2 was going up. And so, the CO2 effect was helping plants get greener. And the other negative impacts, by the way, higher temperatures themselves make it harder for plants to grow. Drought and floods, all those other effects also have an impact. But this research says the vapor pressure deficit is the main thing. So let me read you what vapor pressure deficit is from Wikipedia. And let me think about this for a second. What should I could share a screen so we can all look at this, right? So,
Yep, that's the beauty of video.
That's
you can share
video. So I'm
screen.
going to view that's a vapor pressure deficit. I'm going to try to share the screen. Safari vapor pressure deficit. Let's see. Share. Now tell me if this is all you're seeing. You should only be seeing vapor pressure deficit and nothing else.
That's what I see.
Good. Okay. So the vapor pressure deficit, or VPD, is the difference or the deficit between the amount of moisture in the air and how much moisture the air can hold when it's saturated. Once air becomes saturated, water will condense out to form clouds, dew, or films of water over leaves. In this last instance, it is this last instance that makes VPD important for greenhouse regulation. If a film of water forms on a plant leaf, it becomes far more susceptible to rot. Oh, far more susceptible to rot. On the other hand, as the VPD increases, the plant needs to draw more water from its roots. So what happens is, as temperature goes up, as global warming increases, and now we're this year at around 1.5 C warming, that increases the capacity of the atmosphere to hold more water. And we've seen this happen with, the more floods and things like that, more intense rainfall. Although the average precipitation hasn't really changed much, but the extremes have. But as the atmosphere can hold more water, the amount of water vapor in the atmosphere, even if it goes up, if it doesn't go up as much as the atmosphere can now hold, then vapor pressure deficit increases. In other words, if the temperature goes up, it makes the atmosphere able to hold more water. And if the amount of water doesn't go up that much, then the difference increases. And that's what causes problems for plants, because as it saturates, that's when water can condense out of the atmosphere and form water on the leaves and everything. And the leaves can get that water and use it for their growth. Otherwise, they have to draw water from the ground. But the water in the ground is decreasing because as temperatures increase, the amount of evaporation from the soils increases, right? That's where the increased water in the atmosphere comes from. Well, it comes from the oceans as well, but it also comes from the ground drying out from the increased temperature. And the water doesn't disappear, right? It doesn't vanish. What happens is if the soils dry out, that water's in the atmosphere. And again, so the atmosphere does hold more water, which is a good thing for the plants, but it's not as much as the atmosphere could hold. And again, it's when the water vapor is at the amount that the atmosphere can hold, that's when then water condenses right out of the atmosphere into dew and things like that. So that's what water vapor deficit is. Let's see if I can get to, is this it? No, Scientific American. Where did Scientific? Oh, here it is. So this is the article in Scientific. Are you seeing now the Scientific American article? Because I'm not really.
Yep, I can see it. Or Stop Getting Greener 20 years ago.
Good. Okay. So this is it from Scientific American, but what I want to do, that this is just an article about this particular thing in Science Advances, and increased atmospheric vapor pressure deficit reduces global vegetation growth. And let's read the abstract, and then I'll just give a little more information on this. So atmospheric vapor pressure deficit, which we just talked about, is a critical variable in determining plant photosynthesis. Synthesis for 4 global climate data sets reveals a sharp increase of VPD, or vapor pressure deficit, after the late 1990s. In response, the vegetation greening trend indicated by a satellite-derived vegetation index, which was evident before the late 1990s, was subsequently stalled or reversed. In other words, the Earth was getting greener and then it stopped getting greener. Terrestrial gross primary production, derived from 2 satellite-based models, so that's sort of how much plant growth there is, exhibits persistent and widespread decreases from the late 1990s due to increased vapor pressure deficit, which offset the positive CO2 fertilization effect. That means, more CO2 helps plants grow more. 6 Earth system models have consistently projected continuous increases of VPD, and that's a bad thing. That's increasing the deficit throughout the current century. So they expect the VPD to keep increasing. Our results highlight that the impacts of vapor pressure deficit on vegetation growth should be adequately considered to assess ecosystem responses to future climate conditions. So that's that. And then I have some more notes here on this article here. Here we go. Well, first of all, before we go any farther, anybody have questions on anything said so far?
I think my only thing is just to play devil's advocate, measuring the greenery, is there any thought to the density or type of vegetation that there is? So for instance, if you swap out, if you cut down a redwood forest and just have ground cover or something, would that look the same from above? Like, is there, I mean, and obviously that's a stark contrast, but is the height or density of the vegetation taken into account, or is it just simply the amount of green that we see on Earth?
Well, I think it's the amount of green you see from space, so looking down. So it's probably fairly two-dimensional, but I don't think there's, we're talking about a global average. So if you're looking at a particular place, you might say, well, that's still green, but there's less forest, so there's less mass, you could say that. But I think what they're doing here is just looking at the entire Earth. So it kind of averages out. And if you just have less green where you should have green, or you had green before and it's not green now, that means things are drying out and you're having less vegetation overall. So I think it's,
or a city has been built or whatever that is taken over.
Yeah, but that's still
city
built.
Yeah, sure. Yeah. It's all.
Although I don't know. I mean,
Yeah,
I think they can look at individual places too. So it's not just like cities. Yeah, go ahead. Whoever is speaking.
Several caveats to this are that, first of all, you can measure the intensity of the chlorophyll peak. And the second is that satellites don't just look down. There are oblique views where you can see sideways. So they can get data from different angles, and they can get data of the chlorophyll and other spectral peaks. And the intensity of those peaks provides a semi-quantitative indication of the amount of vegetation, as do the angled views as well.
Okay.
Oh, that's a good point. Right. You're not just looking, I mean, you could just look, straight down, but you're also seeing it from different angles, which would be able to then sort of give you an idea of the height, depth, whatever of the vegetation.
Correct. And in fact, even in one image, you're looking down at one pixel. But when you go to the corners of the image, you're looking at an angle, since the satellite's very small compared to the size of the land being imaged. And so there are several effects, and those can all be taken into account in providing a semi-quantitative indication of the biomass available in any given square kilometer.
Mm-hmm. And it's funny, I worked on, I mentioned 1979. I guess it was 1978. You know how old I am, that I was working on Landsat at Hughes Aircraft Company. They built the satellite. We had a problem with one of the sensors. They had, I mentioned different spectral bands or different colors that they look for, but one of them was infrared, so heat. And there were two sensors on it. One had broken off, had the little sensors, one little tiny wires, right? And one of the wires had broken off in space, and so that one was no good. And the other one was kind of starting to come off, but it wasn't off, so it was giving a very noisy signal. And so what we did, and this is some of the first uses of image processing in space, for space things, was we filtered those images to make them look nice and clean. And it worked quite well because it was a scanning thing, so like a TV scan. And so the frequency of the noise in one direction was the horizontal direction was very different than the noise in the vertical direction. And the vertical direction, it was sort of smooth because the frequency of the noise, it sounds very technical here, but the frequency of the noise was small compared to the scan lines. But on a horizontal basis, it was kind of going up and down very noisily. But we could, since we knew we could average between the pixels above and below, we ended up filtering out the noise quite well and made them look very good. That's not quite, and back then I remember looking at this, how people were starting to trying to figure out what crops were there by their spectral signatures, like how much corn was in an area or how much tree cover there was. So this was all the very, very beginning of all of that back then, because these satellites were brand new. Now they're on the fourth, fifth, or sixth generation of these satellites, which are far more sophisticated, far higher resolution. Back then, if I remember correctly, the resolution was maybe a meter, 2 or 3 or something, 10. Each pixel was 10 feet or 20 feet.
Yeah, a fraction of a kilometer. Yeah, it got a lot sharper. By the way,
now you're down to 6 inches, a foot, that kind of thing now. But
yeah, the infrared band is particularly attuned to plant growth. I seem to recall that plants are dark in the infrared, and so that's a particularly useful band for looking at them along with the chlorophyll bands.
Right, and animals, you can spot. That's why you can take infrared goggles and it all looks black. But if any person or fox or rabbit is walking by, they have their bodies giving off heat, and they show up as white on an infrared signal.
Yeah, and I think plants show up dark on the infrared because they are cooler during the day because they're evapotranspirating more. In other words, they're getting off their moisture to the atmosphere with this deficit of water vapor. And they probably stay cooler than dry land because the dry land's heating up.
Mm-hmm. Yep. Yeah, and you can see all of this. And I'm used to fool around with this way in the early days. You could buy infrared film for your film camera. And actually, in that case, trees came out white. So there's kind of the opposite there. But I don't know what the film response was. The film response itself could have been opposite as well.
Yeah, I think they came out white in the negative, maybe.
Yeah. Oh, yeah. Maybe the negative was dark. I don't know. So I'm not sure what was going on there. But that was certainly the early days. Okay. So here's a little bit more on this. Gives you kind of an overview to get a little more detail here. Vapor pressure deficit, which describes the difference between the water vapor pressure at saturation and the actual water vapor pressure for a given temperature, is an important driver of atmospheric water demand for plants. Rising air temperature increases saturated water vapor pressure at the rate of approximately 7% per degree Kelvin or per degree Celsius, according to the Clausius-Clapeyron relationship. Sounds cool. Good name. Which will drive an increase in vapor pressure deficit if the actual atmospheric water vapor content does not increase by exactly the same amount as saturated water pressure vapor. That's what I was saying before, the temperature can hold more water at a higher temperature, but maybe there's not enough water to make it totally increase by that amount. And that's where you get a vapor pressure deficit. Numerous studies have indicated substantial changes of relative humidity, which is the ratio of actual water vapor pressure to saturated water vapor pressure, not only in continental areas located far from oceanic humidity, but also in humid regions. Although the long-term trend of globally average land surface relative humidity remains insignificant, a sharp decrease has been observed since the year 2000, implying a sharp increase in land surface vapor pressure deficit. However, the causes of changing atmospheric water demand are still unclear. Changes of water pressure deficit are important for terrestrial ecosystem structure and function. Leaf and canopy photosynthetic rates decline when atmospheric VPT increases due to stomatal closure. Hold on, here we go. Somebody in. Closure. A recent study highlighted that increases in VPT rather than changes in precipitation substantially influence vegetation productivity. Increasing vapor pressure deficit notably affects vegetation growth, forest mortality, and maize or corn yields. In addition, rising vapor pressure deficit greatly limits land evapotranspiration in many biomes by altering the behavior of plant stomata. Given that the global precipitation is projected to remain steady, the changing vapor pressure deficit and soil drying will likely constrain plant carbon uptake and water use in terrestrial ecosystems. However, the large-scale constraints of vapor pressure deficit changes on vegetation growth have not yet been quantified. In this study, we determined the changes in VPD trends through observation-based global climate datasets, and then quantified the impacts of these vapor pressure deficit changes on vegetation growth and productivity using satellite-based vegetation index and leaf area index, tree ring with chronologies, and remotely sensed estimates of gross primary production, GPP. So there you go. Let me see, I should have put this, this is what I was reading right here, by the way. So you could have read along with me. So that's what's going on. And this just also shows that climate is complex. And while the deniers just want to say, hey, CO2 is plant food. So climate change, burning fossil fuels to increase CO2 is good, period. End of story. Not taking into account that higher temperatures, so CO2 does help plants, weeds especially, by the way. But so that's one positive thing. And then you have the negative things. You have this new thing, vapor pressure deficit. You have higher temperatures, which slow plant growth and make it impossible for plants to grow over a certain temperature. You have droughts and floods, both of which hurt agriculture and plants. You have fire danger, which is destroying incredible amounts of forest. For example, in Canada this year, I believe it might have been last year, but this year or last year, the amount of CO2 given off by forest fires, which was a gigaton, that's like 1/40th of all of humans' emissions, was more than the total emissions of Canada from the year before, which was something like 0.6 something gigatons. So forest fires obviously reduce, biomass by burning it, but also contributes to greenhouse gas emissions, and that's one of the feedback loops. So that's a positive. That's a amplifying feedback. You don't want to use the word positive feedback because it sounds like that means good feedback, but it doesn't mean good feedback. So an amplifying feedback is one where something causes something, and the thing it causes the original thing to happen even more. So, putting out greenhouse gases and warming the planet causes more greenhouse gases to be released from burning trees, which causes more warming, which causes more trees to burn, which causes more warming. So that's an amplifying feedback. And I think this is another amplifying feedback, that warmer temperatures cause more vapor pressure deficit, which causes plants not to grow as fast as before, which means the plants don't take up as much CO2, leaving more CO2 for the atmosphere, which causes more warming. So that kind of thing. Although I haven't seen this, I don't think this is factored into IPCC calculations, for example, of future warming. Even though.
So an additional point
Hey, Eli.
is that higher rates of evapotranspiration also, tend to counteract the vapor pressure deficit, but that isn't good because that just means that there's going to be less soil moisture, which keeps things cool, or this is the cooling process actually, and more water vapor as water molecules in the atmosphere, which are potent greenhouse gases. So if you think about it as shifting the partition between soil and atmosphere in a way that leads to more water being up there to act as a greenhouse gas.
Okay.
Yeah, and I think this also highlights why they're actually discussing vapor pressure deficit and not relative humidity, because you can maintain constant relative humidity, but in a higher temperature world, there's a larger vapor pressure difference between saturation and the actual moisture level. And so that's interesting that the plants feel the vapor pressure difference and not the relative humidity, which is significant. And then furthermore, this simply confirms that the rate limiting nutrient for plants is not carbon dioxide, it's moisture for terrestrial plants. And that's a very significant, it's good to confirm it, but effectively in most ecologies, a class of species will have a limiting nutrient. And in this case, it's water for terrestrial plants and not carbon dioxide, because carbon dioxide is everywhere. And so in many processes, the plant growth is limited by the limiting nutrient, in this case, water.
Yeah. And
a side note on that, I was going through a review of the various models that try to estimate the effect of higher atmospheric CO2 on primary production, and the model, it's a bunch of different models by a bunch of different people, and the model that showed the least carbon dioxide fertilization effect was actually the only one that explicitly modeled the phosphorus and nitrogen cycles, which should alarm people, because it's saying that all of these other ones are just like making an assumption about two important nutrients, phosphorus and nitrogen, and just kind of going with it. And as you try to treat them more accurately, the number comes out lower.
yeah. By the way, I'm looking at the live stream. It's still only JP and I have no idea where it's at, by the way. Oh, no. Okay. I'm a little bit behind.
Yeah, the limitations resemble a lot more compressing logic functions than they do any kind of linear combination. There's really a saturating effect for non-limiting nutrients. And so, or let's say the limiting nutrient creates the saturating effect that limits the growth, with and the response of all the other variables. So I've seen it where those limiting nutrient relationships are more like logic gates, and they're non-linear and constrained by the limiting nutrient typically.
Yep. And the theory, by the way, for iron fertilization of the oceans is that the limiting factor for algae and plankton growth is iron. So sprinkling some iron in the ocean will all of a sudden cause a large growth in algae and plankton, and then some of that will die and sink to the bottom of the ocean and take the carbon with it that it used, because it uses carbon from the atmosphere in the ocean to grow. And so that would help. That's the theory, by the way. That's not, I don't think it's been shown that would actually work well. If the fish eat it before it drops to the ocean, then you lose whatever. It stays in the biosphere and doesn't leave the biosphere.
Right. It's a limiting nutrient for 10 to 20% of the ocean, what they call the high nutrient, low chlorophyll portions of the ocean. the entire ocean's been mapped according to limiting nutrients for most phytoplankton, and it's largely nitrate limited in the subtropical Pacific. Sometimes it's phosphate limited in the Atlantic, and then up in the Siberian Sea and down in the Southern Ocean, they call those high nutrient, low chlorophyll regions, and those can be iron limited. So it is interesting to look at the limiting nutrient for these different zones in the ocean. There's even a zone around the Galapagos somewhere that claim is vitamin B12 limiting, which is very interesting. So there are very interesting differences in nutrients for a variety of phytoplankton.
Mm-hmm. So,
Well, not
yeah,
not
go
only
ahead.
that, there's the B12 and there's pseudocobalamin, and different species can use different ones, and that actually becomes important for ecological competition.
Agreed.
Hey, Bev, you have a question or comment? Bev? Well, I'm not hearing you.
It says connecting to audio on her.
Oh, yeah. Hold on a second. You're not connected yet for some reason.
So I'll just quick jump in there.
Go ahead.
So do we need supplements for the ocean, or is it, as Eli said, no, the particular deficits actually are needed for biodiversity?
I'll say yes and no. The conventional wisdom is you have to supplement or add inputs to the ocean. But the beautiful thing to understand is that if you just go 100 meters down or 200 meters down, you've got replete nutrients in the mesopelagic waters. And that's really been the beauty of marine permaculture, is realizing we don't have to add anything to the ocean. We just have to restore natural upwelling and give nature half a chance, she'll rebound exponentially. And so this is really about restoring the upwelling of nutrients to the surface waters, the epipelagic zone, as they call it. And that enables the microalgae and the macroalgae to grow, and it brings back the primary production that we've lost 30 to 40% of in the subtropical oceans over the past century.
How do we
Hey.
increase natural upwelling?
We
Okay,
use
we have Bev
renewable
is
energy.
okay. Hey,
Just in
Bev,
a
you're
nutshell,
connected now.
it's renewable energy, and marine solar, wind, and wave energy do a great job of restoring natural upwelling in a variety of ways. And check out marine permaculture for more details.
Okay, Bev, let's go try you again here. I think it should work. You're on mute though, so you have to unmute. You're still muted.
Oops,
Okay,
there we go.
There you go. All
Okay,
right.
hooray. Glory, hallelujah, praise Jesus. Sorry. So a couple of questions. One, on my property here, so in those atmospheric rivers that we had in the Bay Area, well, I noticed that I got an awful lot of, I got different plants that grew a lot. There's some plants just grew like crazy. Yet I didn't have my, and then on the yield on the various fruits, on my main yield on my grapes was not so high, not very high, because it didn't seem to be affected by the water, but by the extra rain. But it was also, might be the age of the vines, because they're 100 years old now. But also, I noticed some plants, some apple trees and various other fruit trees, they have, some have real high yields this year, and some have a lot lower. That's interesting. And then the other, I was interested in the answer to the question that Philip put in the chat about the nitrogen, what the effect of nitrogen is. Thanks.
Okay.
Yeah, so I can say that just as an intro, to quote Alan Savory, he said, "It's not how much rain that matters, it's what the land does with the water." And if you have beavers, then you slow down the water and you spread it out, and it gives it more time to percolate into the ground. Whereas if it's already really parched and dry, a lot of times it'll just sheet off and go into the rivers and just cause floods down the rivers. So it really is about having a porous and permeable soil, which is generally done by earthworms and not tilling and not compacting the soil. So it's very much about how you cultivate your soil to actually be porous and permeable. to be able to absorb a lot of rain when it does rain.
Okay.
Okay,
Wait.
so that could
Yeah.
explain, that could explain it. This, we've been in 3 years of La Nina here, and we don't till. There's no tilling. I mean, there hasn't even, well, there's been some tilling, but, no, I mean, some mowing, but no tilling. So we've got, should be permeable, but I also have, topsoil that's varying degrees, varying depths going, as you go
Yeah.
front to back of the property. Yes.
Yeah, I
Yeah,
also
what
don't
I
think you
learned-
can really take into account this global average vapor pressure deficit as being something that's impacting you in the Bay Area. You're near the ocean, you're going to have different
Mhm.
humidity profiles than other parts of the world. And there's so many other local factors that could be bigger than this one.
Yeah.
On average, since those other things that are particular to a particular place average out over the whole globe, you can see the vapor pressure deficit impact that's applied, which might be affecting you a little bit, but maybe these 100-year-old vines or something else have a bigger impact, right? So
Yeah.
you have to, it's hard. It's hard to take one of these global things and apply it to you locally when there's a lot more noise and variability
Yeah.
in your own
Yeah.
particular situation. So
One
that's why
local
they
lesson
take a look
that
at the
is-
whole satellite record and see what's happening across the
Mhm.
whole world.
One local lesson that is valuable is that ground cover will protect soil. In other words, even from the landside images, when you've covered, even with a winter crop or some stubble, even crop stubble, will reduce the amount of soil evaporation that occurs. And so one of the main lessons is to keep your ground covered. Basically, don't mow too short. Partly because you want to keep that plant vegetation above the ground so that it will, when the sunlight does shine on it, the plants will evapotranspirate and not the soil. And
Yeah.
if you have trees or silvopastures, the trees do a great job of actually keeping a canopy, avoiding direct sunlight on the soil. And we've got trees that create their own little moisture sphere. You've got the tree's big enough, it'll create a little shadow that will keep it moister underneath the tree than it is elsewhere. And so that ground cover is a key thing that Landsat observes and that you can apply locally to your own property as well.
The thing that's the main water retention mechanism for soil is the mycorrhizal fungi. The mycorrhiza relationship with root systems. It's the mycorrhiza that break down the sand and decays dead plant matter and organic matter, converts it into nutrients, which then feeds the root systems. It's also the thing that retains and abates the water in the soil, that soil microbiome. It's the most critical factor for that. The mechanism for evaporation, why this vapor deficit is a big deal for plants, is that the trees draw water through the root systems via the xylem tubes that are in the middle of the trees. The leaves have to, for that vacuum, that negative pressure space to exist, the leaves have to evaporate off the water as it's coming in, because that'll create the negative pressure in the xylem tube, which is the mechanism that it uses to draw water up. If the water can't evaporate because it's reached a saturation point, then it can't draw water up into the leaves to cool them off from photosynthesis, because like the sunlight only penetrates the first couple layers of a leaf, and then that transevaporation is bleeding off that excess heat.
Yeah, but I think
So-
they were saying in this article that actually is a negative thing, is that when the vapor pressure deficit increases, then plants have to draw more water up from the roots. I mean, that was what they're saying. And that's a negative. I guess it's better for the plants to get it from the atmosphere if it can. And so that's why they're saying that the plant growth was decreasing. That
Yeah,
was the
keep
basic
it-
mechanism.
When that vapor deficit hits the threshold, the stomata of the leaves close,
Right.
just like the pores in your skin close. And then you're probably getting reduced production after that.
Right. So-
Specifically because it's the stromata that is how plants take up carbon dioxide. So you got to close them to to not lose too much water, and in the process you're not taking in the extra carbon dioxide that everybody had been hoping plants would take up.
Yep. Well, that's a good way to put it. I also understand that once CO2 gets too high, they also close up because they don't want to take in too much CO2, and that's another problem. So this whole idea that, more CO2 is good for plants, no matter what, is not real. So by the way, so I think there's some things, well, let's see. Looks like Philip raised his hands. Go ahead, Philip.
Yeah, thank you. Thank
Philip,
you,
you're on
Dan.
mute.
My question relates to nitrogen and phosphorus. Can you?
Okay, now I can hear
just
you. Now I
check?
can hear you. Okay.
Can you hear me?
Yeah, good. Yes, we
Can
can
you
hear
hear
you
me,
now.
Dan?
Yes. We can hear you.
Yeah.
Go
Okay,
ahead.
I'm asking
Nitrogen
about,
and forestry is what he said, Dan.
no, nitrogen and phosphor. I'll put my answer in my question in the chat. Thank you.
All right. We were hearing you there at the end, Philip.
Okay.
Just
then
starting
I'll
off was
try
a little
again
bit
one
hard.
more time. Okay, I want to ask about the importance of nitrogen, and especially nitrogen, but also phosphor. And I heard Dr. Brian talking about how moisture is a major inhibiting factor for tree growth, and because there's so much carbon dioxide. But what about nitrogen and the fact that we've de-wilded to such an extent that there's so much less animals and so much less natural net nitrogen being inputted to the system? And I'm just wondering how much of an effect that has. And then as a last question, why does nitrogen and phosphor classify as their own planetary boundaries? Thank you.
Mhm.
Right. Yeah. I think the reason it's classified as a boundary has to do with the human production and application of nitrogen and phosphorus. But it's important to understand that if you have a healthy, biodiverse community of microorganisms in the soil, they will produce available nitrogen and phosphorus in two ways. One is there are nitrogen fixers in the soil, so that when you have a healthy, biodiverse soil community, you can actually convert dinitrogen in the atmosphere into nitrate and ammonia, perhaps, in the soil with those nodules that actually fix the nitrogen, which is very profound. The second thing is, if you have those mycorrhizal fungi and other kinds of fungi, they excrete enzymes that will dissolve mineral phosphorus and convert it into bioavailable form. And then they use those mycorrhizal highways to convey the phosphorus and the nitrate to the roots of the plants, where they exchange the nitrogen and phosphorus for complex sugars coming from the plants that then later gets turned into humus. So it's a great opportunity. And the challenge is, if you put a lot of nitrate or a lot of phosphorus into the soil, it's like giving a kid sugar. I mean, sure, they'll get wired up for a while, okay, but it actually shuts down a lot of the biological processes. And furthermore, if you apply glyphosate, which is classified as an antimicrobial, it will actually wipe out a lot of the beneficial communities. So that better life through chemistry business about the green revolution, well, it was actually creating pH intolerant soils and wiping out a lot of the biological biodiversity. And so it's this deeper biological understanding of the soil that I believe will lead towards understanding how a lot less application of nitrate and phosphate is possible to have healthy plant communities in terrestrial environments. Thank you.
So Philip's asking about how important our animal life. We've lost 70% over the past 50 years. I think mammal, weight is still pretty high because of cows and other species that humans breed. But even though the amount of wild mammals have dropped tremendously, and there's only a couple percent of all mammal biomass right now, which is pretty crazy to think about. I don't think it, I think it's really important for ecosystems. I'm not sure it's important for what we're talking about here in terms of carbon uptake. because again, I think these other animals are taking up a lot of carbon, even though they're creating methane at the same time. So cows, at least. JP, you have your hand up?
Yes, so this is on behalf of Lightning Rod on YouTube, from Thunder Bay, Canada. He's asking about the previous discussion. He's asking any thoughts on what will happen to 15 million square miles of burnt. And he said
Say
that,
again. What's going to happen to what now?
15 million square miles of burnt with a capital B.
Oh, the
I
fire
missed the
damage.
word there. Yeah, and he said that Siberia have dried out dramatically over the last 10 years, so the whole top of the world. Canada has a 300-year tree strategy for forestry management. He said he's not clear on how money is made that way.
It's 2 hours.
By the way, I'm changing the subject. I'm looking at the stream, and it says it's private. I set it for public, but it's like not, and I can't even change it.
Question regarding the burnt question, I think, you will in the near term see a lot of little saplings growing out of the char, just because char does tend to stimulate the soil. But the huge deficit that Dan mentioned, I mean, a gigaton of carbon dioxide lost this year. I mean, it's just astounding, the percentage and the reservoirs. I mean, I think I saw a recent chart that said, that deforestation is a bigger contributor of carbon dioxide on a particular time scale than even coal burning, on a year-by-year basis or something. So we have to look at this deforestation effect as being as profound as coal combustion when it comes to our CO2 balance. This is Brian.
And that's both the deforestation that's kind of starting to feed on itself, like in the Amazon, which is increasingly becoming savanna instead of tropical rainforest. But also, there was a paper that was from 2022 that still found a significant carbon dioxide fertilization effect, but also observed that a lot of that was wiped out by land use changes. And similarly, the National Forest Service in the United States, which is focusing on forests in the United States, has found that both the changes in soil and in land use are going to mean that what have been regarded as a potential sink are instead going to be a source of carbon dioxide fluxes by 2070. So, the notion that plants will save us is not panning out on the course that we're on. And that was supposed to save us from all of the carbon that soil will release at higher temperatures, right? So I think this has been a blind spot, and we're on course to be blindsided.
Yeah, sorry, I'm trying to figure out how to how to get the YouTube thing to be public, and I think we're giving up on the YouTube for this time. We're going to try again next week with I think better streaming software that gives us much more control over what's happening here. Because
So you're saying, Dan, it's not discoverable because people have
it's
joined.
private. I think if you have the URL, which I guess I published,
Right? Yeah. So
it
it's
says private. I don't know what private could mean different thing, but private usually you need to have the URL and you can't discover it. So anyway,
Right.
that's okay. That's actually okay, I guess. But still, I don't want it to be that way. I want it to be a public
yep.
stream. And eventually we want a lot of people to be on here, and it's not going to work the way it's set up now. But it's a step forward where this is the first time we're trying it.
Yeah.
And next
we
time
should
we'll
test it out during the week or something.
Yeah, I did do a quick test of the streaming, but not all integrated with all these three things happening at once. So,
and I totally forgot now that we're doing it this way. Like I'm typing up the links and stuff that people have dropped in the chat and that you've referenced and whatever, and I'll just.
So one really cool thing about Zoom, which is very cool, is it has an AI note taker, which I think is turned on now. And it really works really well. It says, Stacy said, I'm taking notes. And then Dan said, well, there's this AI,
Oh,
and it gives you a typed summary of the entire conversation, which
that's
is
funny
searchable.
That's so I said, I did that I said, I asked you to enable.
Yeah, and that's how I saw it.
companion.
Stacy is requesting AI companion and enable. I
Yeah.
thought, but I thought it was already on.
When you said it, that reminded me of last week, and but I didn't see it running. So
Maybe not. I turned on something that I thought was that.
well,
but,
good. No,
so now
it says stop. It says summary. Like, so it's like it's happening. I just am not seeing where it is yet because I'm
okay.
not.
I saw it.
What?
I saw it after the last room. I saw it. Anyway, we'll figure all that stuff out. I still think that maybe Zoom as a base, although this new streaming software might have its own Zoom-like capability that might be more oriented towards a webinar style, which Zoom also has, but this is not that. I think you need I have a Zoom subscription, but I don't have a webinar Zoom subscription. And I think it runs the room slightly differently.
Yeah. You have to
But
bump
before
it
we
another
switch
level
over
up.
to Zoom webinar, we'll try out this other thing. Speaking of these kinds of things, I'm going to be on a podcast. Well, I'll be recording a podcast tomorrow with Adam McKay. For those of you who don't recall, Adam is the producer and director of Don't Look Up, and also Anchorman, Vice, The Big Short, and he's the producer of Secession, which obviously is a very popular show recently. And he's all in on climate and has set up something, we've talked about this before, something called Yellow Dot Studios, which is creating climate content, especially short form climate content for like posting on social media. And he's doing a podcast on climate. I think this is the first one, and I'm one of the guests on it. I don't think it will be playing tomorrow. I think they're going to edit it together and then post it. So probably next week I'll be able to tell you where to find that. I assume it will be posted by then. So we'll see how that goes. And next week, again, we're going to try a different combo of technology here to see how we can really make this thing work. Oh, we're getting a good turnout on Zoom, though. That's better than last time, and that's good. And then in terms of, let me get to Club Deck again. We have 16 there. Again, anyone there on Club Deck, if you want to come join the conversation on Zoom, the link is at the top of the room, and you can click on that and then join the discussion. You can ask a question. By the way, is there still, room chat? Let's see. Frank was posting a lot of things, but greetings, beautiful humans. Okay, well, thank you, Diana. All right, so I'm not really monitoring the room chat on Club Deck, so come to Zoom if you want to ask your question. So I think we covered this one, the vapor pressure deficit. It's just another example of things that we don't know. Well, if we thought about it way ahead of time, maybe we would not have thought of this as being an important thing. And there's going to be a lot of stuff like that we're going to find out. At higher temperatures, oh no, this happens. Like, we didn't take that into account. This feedback is kicking in earlier than we thought, or whatever it might be. And the bottom line is, you don't want to screw around with the earth like this. You don't want to play these games where you do a big experiment. Hey, let's increase the CO2 content of the atmosphere by 50%. And actually, let's double the greenhouse gas forcing of the atmosphere, and let's see what happens. That's an interesting experiment. Okay.
Let's hide what we're doing with sulfate aerosols for several decades and then cut them off rather suddenly.
Yeah, let's do that too. Speaking of that, I do want to, let's see, I can share, I find this again. NASA. So let me see, share. this. So Jim Hansen, hold on a second. Jim Hansen wrote an article way back when 2007 called Scientific Reticence and Sea Level Rise. And I'll just read you the abstract. I suggest that a scientific reticence is inhibiting the communication of a threat of a potentially large sea level rise. Delay is dangerous because of system inertias that could create a situation where future sea level changes are out of our control. Situated with future sea level changes out of our control. I argue for calling together a panel of scientific leaders to hear evidence and issue a prompt, plain written report on current understanding of the sea level change issue. And basically what he's saying, and this is unfortunately true, that climate scientists have an incentive not to say how bad things are. There's actually a built-in incentive in the entire scientific industry, which in general is generally a good thing when you're talking about, you know, do black holes exist or this or whatever. It sort of like stops the worst case kinds of suggestions from being presented, which is fine for most kinds of things, but it's not okay for climate change. And for example, the reason is, I mean, putting it maybe overly simply here, if you publish something that ends up being wrong, it really hurts your career as a scientist. If you don't publish something that turns out to be real, nothing happens to your reputation. You know, so let's just say you think sea level rise is going to be, could be with there's a 20% chance that it could be 10 feet of sea level rise. And you're 95% sure that it'll be at least 3 feet. You're going to publish the paper that says it's going to be at least 3 feet, but you won't publish the paper that it might be 10 feet because you want something to be within, you want 95% certainty for anything you publish. That's like 2 standard deviations, as they say. So 3 feet, greater than 3 feet, hey, 95% certain, I'm going to publish that. 20% chance of 10 feet is unbelievably catastrophic. And the fact that it's even 20% chance is crazy. You know, think of yourself as you're flying a plane and there's a 20% chance that the plane's going to crash. I mean, you'll do everything, you know, declare Mayday, you'll find the nearest airport, you'll do everything to land as quickly as you possibly could, even with a 1% chance of crashing, right? And yet, because of reputations and other factors, scientists are sort of urged not to publish information, even if it's a 50% chance of happening. Now, more and more, they're stepping out to do this. In fact, next week's climate chat, which I can't talk too much about yet because it's an embargoed paper, but there's a new paper coming out with scientists warning of what's happening with climate change. And it's going to be released this week. So keep your eye out for that. But we'll talk about it at next week's climate chat. But so there's more of that happening. But in general, when you're publishing a paper, you need to be very, very sure of what you're saying that can be proven right. But when you're talking about existential threats, a 50% chance of some catastrophic thing happening, and yet you don't want to publish it because it's only a 50% chance, this is really screwed up. And this is what part of what Jim Hansen is getting at here. I will push this onto the Zoom chat. Let's wait. Where's my Zoom?
Here in Australia, it's called the tall daisy syndrome, and it just that the tall daisies get mowed down and don't stick your head up, which is unfortunate.
I'm going to post it also into Clubhouse. Here we go. So check out that article sometimes. It's very, and this is something Jim wrote long ago.
I like that. And actually that was a nickname for me at one time, is Daisy, but I am short, but actually, I guess I act tall. That's
Okay. And on Zoom, no one can tell anything. You look tall. Your head is near the top of the screen there. You look very tall, and there you go. So
This actually enters into the psychology of how we're going to respond to climate disruption. In particular, very few people get fired for missing a call. But if you actually say something is going to happen and it doesn't, then you're to blame. And this extends to many, if not most, of our social institutions and the kind of whack-a-mole philosophy. And what could we? And so it raises the question: what could we change in the way we govern our institutions to alter this outcome? Because at a fundamental level, you could say that a number of excesses and unsustainability in civilization is due to our behavior, and some of the behavior is a lot.
But it's not just our
CO2.
behavior; it's our response to the changes, and that's why. So that's why the airline industry actually took this on. So it used to be after planes used to crash because their things were wrong with them, but they made that better and better and better. And then finally, the number one cause of air disasters was called CFIT, CFIT. Controlled flight into terrain, which meant the plane crashed because the pilots flew it into the ground or into a mountain. There was nothing wrong with the airplane. Nothing wrong with the airplane. The plane, just the pilots got disoriented. There was fog, whatever it might. They didn't know what was going on, and they made mistakes. And sometimes, and there was a famous one, which I might have triggered it. It was really interesting. I want to say it was Delta. I don't remember. It was landing in Florida, this plane. I think it was a DC-10. It was a long time ago. And they had the recordings of this. So the plane is coming in for a landing. And all of a sudden, the alarm goes off in the plane saying, pull up, it says glide slope, which means the plane is flying too low for the landing. And the pilot said, turn that off. And so he turned off the alarm. And then it goes off, glide slope, and he kept saying, turn it off. Finally he said, turn off the circuit breaker for that. Like, turn off the alarm system that's annoying me here. And then they did that, and then the plane crashed into the ground because the guy was flying too low. So the plane is yelling at him to pull up. You're doing this wrong. And the pilot's so confident about his flying ability. And then very importantly, the first officer was concerned that he was flying too low. But back then, there was this deference to the pilot. And so, the pilot was in command. You were second to him. You don't, and you can obviously see how this pilot's reacting to the alarm. And the first officer didn't say anything. And so this was transformative for the airline industry, and this is what should be transformative for the climate and politicians. Is what they did is they changed the whole way that what's called crew resource management. So they elevated the first officers so that they not only could say something to the pilot, they had to. In fact, the pilot had to ask. If you hear a tape now of something happening on a plane, the pilot is saying, "I'm doing this," and then the first officer say confirmed or yeah, it was something. He'll confirm. I'm going to shut down the left engine. Shut down the left engine. You'll hear them going back and forth, confirming everything. And this is all part of what's made flying a plane the safest thing you'll ever do in your life. A commercial aircraft in the United States. I mean, there's maybe some countries where it's not as safe, but Europe, and then most of Asia and the United States, because they follow these incredibly strict things and don't allow 1% chances of crashing, they land immediately. And yet we're on this, I call it, if you take plane and add the letter T, a planet, you take this planet, has all our children on board, and we're flying it, and all the alarms are going up. glide slope, and pull up, and we're saying, hey, shut that shut that alarm off. It's exactly the same thing. And it's pretty crazy, by the way. And I'm even feeling it recently because as we've talked extensively here on Climate Chat, recent research, credible research says that the AMOC is on track to shut down around mid-century. That doesn't mean it will. It might happen later, but might happen sooner. And so it's credible evidence that this is happening. It's kind of like the alarm bell going off. And there's like total silence. I wrote to President Biden's climate science advisor, heard nothing back. And you're treated as if you're like the crazy person. We're talking about published scientific research, which matches up with reality. Because I mean, the reason they say it's going to happen sooner rather than what the IPCC said is because the IPCC's models don't reflect reality today. They don't match the temperature profile of the Earth today, the model they're using. So they say, well, let's adjust those models so that they do reflect the temperature profile we see today. And when you do that, all of a sudden the AMOC collapses very quickly. And so it's credible. It's an alarm bell that we should be taking immediate action. By the way, we might not be able to stop it. And if so, we need all the time that's remaining to prepare for it because it's going to screw up so many different things, including an immediate couple feet of sea level rise along the East Coast. Go ahead, Brian.
Yeah, political decision-making timescales are vastly shorter than the timescales that we're talking about. Usually it's the next election. So they've got a time horizon of 1 year to get elected. And until it's the burning issue, literally, of our civilization, it's not going to be really much done about it. The job of a co-pilot, as a pilot for several thousand hours, and NASA Aviation Safety Reporting System has testified, the primary job of the co-pilot is to question authority.
Mm-hmm.
That is what they must do in order to have a safe plane and a safe planet, as you so aptly put. But
that wasn't always the case. That is a change.
It has changed. And what's interesting is several countries had more of this deference going on, and they had far higher fatality rates. And so now they actually had to come to the U.S. for pilot training, and they had to train the co-pilots to question authority. And it works much better now.
Yeah.
And we, as co-pilots of planet Earth, need to question authority. That is our primary job as co-pilots, is to question authority and realize that political decision-making has very little to do with technical reality. And we just need to translate sufficiently for the public and for political decision makers on how dire this is and how this has to become the burning issue of our generation.
But it's not just politicians, it's the media and it's everybody, really. It's the public as well. See, we have Eric. Eric, welcome. You have your hand up.
Yes.
Hi.
I don't know about this upwelling. So I guess it's a two-part question. And Dr. Brian, sounds like you know a lot about this. What is causing us to lose the upwelling? And I guess maybe it's a related question if there's time. I also don't know why the AMOC is likely to shut down. So I guess it's
okay. Well,
thanks.
We've covered AMOC a lot, but the quick and dirty is that the AMOC is think of it as a conveyor belt that's driven by two factors: the heat of the stream of water and the saltiness. So salty water is denser than fresh water, and denser and cold water is denser than hot water. So the hot water, warm water is coming across near the surface. It reaches Europe. It gives off its heat. And then this salty, now it's colder, dives down and then comes back the other way. Think of we're oversimplifying here, but think of a conveyor belt like that. Now, what's happening is there's fresh water coming in from Greenland, a melting Greenland. So there's fresh water happening in the North Atlantic is being spread there. And that's lighter and it's above the this AMOC, and that's slowing it down because it can't give off its heat as much, it can't dive down as much. And that's okay, that would, so it's down 10, 20%. Okay. But the problem is the salt water actually comes from the stream itself. It's saltier, that the AMOC stream of water. So when you slow it down, there's less salt, right? Because itself is bringing less salt because it's slowed down. And that, what does that do? That slows down the AMOC because it has less salt water. And so you reach a point where, you slow down, oh, boom, and then it just collapses because it gets into a feedback loop that's too fat, right? The saltiness slowed it down, which made less salt, which slowed it down, which gets it down to zero, and then it just stops. So that's why instead of just linearly slowing down, it's like been down 15, 20% in 50 years. We felt, oh, maybe in another 50 years, it'll be 30, 40% down. No, in 20, 30 years, it could be at zero because it's going to fall off a cliff, basically. Think of it that way. And that's the danger of the AMOC. And the reason they said it's going to happen sooner is one of the factors that you get when you slow it down is that the temperature of the water around south of Greenland gets colder. So the whole world is warming up. You look at a map, of the globe of the temperature today versus, 30, 40 years ago, you see it's all red, except for one spot below Greenland where it's blue, where it's actually colder today than it used to be. And that's the major effect, is the AMOC slowing down. So they know it's slowing down. Well, first of all, they're measuring it now, but that sign, the IPCC models don't show a cold blob below Greenland. So it's wrong. The model's wrong because that's today. It should at least reflect today, and it doesn't. So when you correct the model so that it does show a cold blob, that also means basically what you're doing is you're saying the sensitivity of the AMOC to freshwater intrusion is higher than the IPCC thought, right? And when you correct for that, there's the cold blob. Okay, that's good. Hey, we got the model to reflect today's conditions. That's great. Now let's run that model into the future. And then you go, oh shit. It shuts down much sooner than the IPCC was saying. And that's the bottom line for what both James Hansen and the Danish researchers that came out with this paper are saying. Now, could they be wrong? Sure. Should we assume they're wrong? Absolutely not. And again, this gets back to something I've talked about recently in the space shuttle. They launched the Challenger, and the reason they launched it, even though it was way below the allowed launching temperature, the allowed launching temperature was 40 degrees. You were not allowed to launch the shuttle if the temperature was below 40 degrees, and the temperature was 26 degrees, which is insane. The fact that they had a discussion to decide whether they should launch is insane. You don't have those discussions. If the launch temperature is 40 degrees and the temperature is below 40 degrees, you scrub the launch. You don't need to ask anybody. It's just, that's what you do. And I'm talking about an unmanned rocket. And I used to work on the unmanned satellite, it's going to be launched, and the launch temperature is below the spec. You scrub the launch. That's it. You're done. You don't have to think about it. That's just what you do. And this was not a little below. This was way below. And on top of that, it almost blew up at 52 degrees the last time they launched it. It had these O-rings had burned through, but they didn't blow up the rocket, but they had burned holes in it. So, and that's why they were redesigning the rockets, because they knew it wasn't working well at low temperature. So crazy, you just look back, you say, well, this is insane. Well, we're doing exactly the same thing right now. We're like, yeah, okay, we see this AMOC report. Yeah, we see that it says we expect, not it's possible. We expect the AMOC to shut down in 20 to 30 years. That's the expectation. And yet we treat it as if, well, it's a scientific report. Maybe it's right, maybe it's wrong, who knows? But this is insane. I mean, you
We
don't do that.
But
Well, you
Dan,
don't do it when it's something, if it's whether a black hole absorbs matter from a companion star or not, okay, maybe you don't care. You take your time, you work it out. 20 years later, some new research tells you what happened. Well, that's fine. But we're
Dan,
talking about
we
the
have-
life systems on Earth here.
We have elections that need to be won. We have campaigns that need to raise money. We have all these things that, so the people that are making the policies that would help to get us out of this are, as previously mentioned, on these extremely short time
yeah.
cycles. And so they aren't motivated to do it
But
because
it's not just that.
it's
I
unpopular.
agree. I agree that's part of it. But let's take another thing that's happening. I was talking with my brother's visiting here from Denmark. Is here this morning. We were just talking about this morning. Something, it seems it's a little bit related. So Tesla is dominating the electric car market crazily. Their Cybertruck is coming out in November. They haven't sold any yet. Ford came out with the Ford F-150 Lightning and said they had 200,000 pre-orders, which was like incredible amount for them. And now they're making them and selling them. And now they're cutting back production because they can't sell any. And they had 200,000. They haven't sold 200,000. So there's something strange going on there. All the legacy car companies are, maybe bankrupt in 10 years because they're not scaling up EVs enough. And yet you take, now it's not politics anymore. Take the investment advisory, supposedly the extremely smart people that give financial advice, to people about what stocks to buy. And they're not treating these car companies like they're Nokia, which, by the way, just laid off, my brother told me, another 14,000 people yesterday. I didn't know there was 14,000 people working there anymore. But and this is super clear. The Tesla Model Y is the #1 selling car in the world, not the #1 selling EV in the world. It's the #1 selling car in the world. And this is all happening right in front of our eyes.
Wait a minute, Dan.
Yeah.
I need a link for that or something. I guess I can
Oh,
Google
no, you
it.
could look
but-
it up. It just
but
type that in.
that's something that is it did not unseat the traditional F-150.
It did.
There's- Shut up. Are you serious?
Look it up. This is this year. This is this year. It's not. It's on track for this year's sales to be more than
The
F-150
F-150 has been the #1 selling vehicle in America. What? Oh, sorry. We're saying the world.
the world. Yeah. By the way, that's the thing. I mean, maybe F-150
Okay.
outsells in the United
Okay.
States.
Okay. Yeah. Because I mean,
That could be.
because anyone who's smart and needs a pickup outside of here, they get a Tacoma or something that's smaller, like they don't get the monster.
But my point isn't that, we could talk about Tesla. It's interesting to talk about it. But my point is there is so much data available to everyone about the disruption of the car industry by EVs. Whether you like Tesla or not, that doesn't really matter. There is this disruption, and it's not something that might happen in the future. It's happening right now. It's as if the temperature is 26 degrees and all the other car companies can launch at 40 degrees or above. And yet somehow, and I don't know how this is possible, that all of these official financial analysts still, they're not sounding the alarm bells that, wait a second. I mean, you can see some people on YouTube and stuff like that just look at the data and say, oh my God, these guys are going to go bankrupt. I mean, again, it happened before with the iPhone. It very quickly destroyed all the other phones that had keyboards on them. Yet for a long time, I mean, it didn't take very long, but it only took a few years to totally disrupt that market. But for a while, everyone said, well, people want their keyboards, even though the data was saying they're getting wiped out and whatever, and then it destroyed Nokia very quickly. And I'm saying the same thing is happening in the cars right now. And whatever that is to have all this data super clear, the S curve, we're on the upswing of the S curve on EVs. And that's like more than 10% sales, which are even the US is now more than 10%. China's at 30%. It's the biggest car market in the world. How can you ignore that the biggest car market in the world is at 30% sales of EVs and going much higher very quickly? So all the data is there. I'm saying the same thing is happening with climate. You can just say it's politicians and their 4-year or 2-year cycle or whatever it might be. Yeah, okay. But it's much more than that. We have all the data. It's very clear. The impacts are now all around us. It's not like saying someday in the future, this extra CO2 is going to do something. No, we're at 1.5 degrees of warming, which was the warning temperature for everybody. And yet, most of the world, including all of the analysts who look at these things, are ignoring it. So it's pretty crazy. And again, I've made my list of reasons we ignore it, and I think there's a lot of that. Let's go on. Brian, I think you were next on the hand raising here.
Answer Eric's previous question. Before we had global warming, a normal amount of wind stress with offshore winds would cause natural upwelling to feed the kelp forests and the plankton forests and all the rest. But in a global warming world, 90% of that global warming is in the surface layers of the ocean. And that actually acts like a lid on the natural upwelling process. The normal amount of wind stress, the offshore winds, will not produce the same amount of upwelling. And that's why we've seen losses of 90% of the Nerecistus kelp forest off Northern California and 95% losses off Tasmania of the Macrocystus kelp forest. And it's all because there's less upwelling, less nutrient supply, and thus less primary production. So it's all about restoring that natural upwelling to get us back on track on more pre-industrial conditions. Thanks for the question.
Oh, wow. And what kinds of things are practical to do besides obviously getting greenhouse gas emissions to zero?
Well, I think the near term is something we're developing called marine permaculture, where we've got a 1/4 acre in the water right now in the Western Pacific. But our goal is to build a full hectare, that's 2.5 acres, that we think is going to be economically sustainable for coastal communities to actually, provide enough upwelling, get their kelp forests going again, and have food and habitat for fish and improve the fisheries. It ends up being economically sustainable. And hopefully we can launch a whole industry based on that and have it be regenerative and helping small communities in thousands of coastal regions around the world. So that's our dream for the Marine Permaculture Alliance in the coming years.
Mm-hmm. Very good. Hey, Bev, you have your hand raised.
Well, so I agree. The politicians aren't doing anything. Then maybe the corporations are coming around, and certainly the financial institutions are coming around because they're losing money like crazy. But what do we need to do? Science is not what I grew up in an era of science. Okay. And it was like, that was really important. And everybody had a lot of respect for it. Now they don't seem to be. There's just, people seem to be ignoring what science is saying. So it seems to me it's about communication. What do we need to do to get this across? Because this is going down faster than we are moving. Thank you.
I'm sorry. Actually, I was posting something. Can you repeat your question? Sorry, one more time there.
Yeah, what do we need to do to get this moving?
Well, that's the $1 million question. That's the
I think it's helpful to understand that people
question.
Don't make decisions based on purely rational means. Ultimately, we should recognize that a lot of people make decisions for emotional reasons and then design our conversations accordingly. Ultimately, we have to really help people understand that caring for spaceship planet Earth matters, and we have to understand that this is an existential question for our civilization. I think I'll quote Sir David King when he said that we've already passed multiple tipping points, and our actions in the next 4 or 5 years will determine the fate of civilization for the next several thousand years. That's how dire it is today. We're past multiple tipping points, and it's really a question of call to action. It's a question of time. How quickly can we organize politically to actually make a kind of difference like we've seen down in Australia, with the Teal candidates actually being necessary to form a coalition government and enable those decisions to be made, they've had a lot more influence in the last couple of years with those political changes. And I think we have to see those in the US as well.
Yeah,
I'm
on
sorry,
that
just a-
note, I'll
just a-
repeat this
Sorry, just
quote.
one quick housekeeping question. You said
Okay.
teal candidates? What?
Yeah, it's not red, it's not blue, it's not the normal left and right. Teal is let's say perhaps economically conservative and yet environmentally progressive, and that's why they use a different color to designate
Okay,
this
Yes,
high. It's
Thank
moving
you.
beyond the linear political analysis to really multi-dimensional analysis, where you've got, you know, environmental concerns and let's say economic concerns.
I think going back to the point that Dr. Bryan made about the emotional components of decision making and motivation to actually take action, we're confronting the urgent half of it, which is, you know, there is this existential threat that is fast approaching, and it's getting worse at an exponential rate, and that is becoming clear to people. However, there are two problems. There's kind of the learned helplessness that we've been in due to the political paralysis, which has been sponsored by the fossil fuel industry and their allies in politics. That we can break through, but breaking through that, I think, depends on engaging people in a somewhat different way, which is not, you know, there's this horrible crisis coming, we've got to do things, we've got to make all of these sacrifices. That all might be true, but the outcome of that narrative is, well, we're not as good off, but we're much better off than we would be if we didn't do anything. Whereas we do have an opportunity right now to get the relationship between humanity and our home planet right, and wind up with restoring pre-industrial climate, restoring pre-industrial ecology in a lot of places, and being able to support civilization more comfortably and more inclusively, so that there aren't a billion people, you know, in precarious conditions of poverty all the time, and, you know, more than 500 million people subject to recurrent hunger. We can do all of that. When they talk about these planetary boundaries, you know, like the nitrogen cycle and the phosphorus cycle, you know, when you go into more details than just carbon dioxide, those, you know, saying that we're beyond the limit, saying that we need, you know, so many more planet Earths to support everybody at the level that Americans live at, baked into that calculation is the same inefficiencies that we support the standard of living of more affluent Americans in. And the point is, that's not you know, physics. That's just what's being convenient in terms of economics, right? But when we make that efficiency, resource utilization efficiency, a circular industrial ecology, a priority, we can do so much better, and we can have a beautiful future. And that is something that will motivate people when they understand that.
Okay.
That's a great.
By the way,
Elon.
speaking of this idea of the data versus emotions convincing people, again, I've read this before, but one of my favorite quotes from George Marshall, who wrote the book, Don't Even Think About It, Why Our Brains Are Wired to Ignore Climate Change. He said that people make decisions based on emotions, not based on data. And his quote is, ironically, one of the best proofs that information does not change people's attitudes is that science communicators continue to ignore the extensive research evidence that shows that information does not change people's attitudes. So I think that is a really nice way of putting it, that, you know, the science communicators who have all the data that says that data doesn't change people's attitudes, they don't change the way they communicate. They continue to present the data, and they ignore the data. So maybe if we gave them a really good story about why they should change their storytelling, maybe that would get them to change.
Yeah, in many ways, negative news is demotivating. It's not directional, it's kind of repulsive. And whereas with a suitable combination of guilt, humor, and small children, and that is the next generation, you can oftentimes motivate people to say, you know, this is the opportunity to help your children and help your grandchildren and make it personal. Because after all, everyone in the next generation is going to be dealing with what we're emitting today.
You know, that's exactly what motivates me a great deal. Is I have 7 living descendants right now, and that what motivates me a lot. And I'm sitting in a room where I could be doing a lot more affluent things, but I'm not, because it's the emotion of wanting to, how can I sit here the rest of my life and just use all the resources that I have and just have a good time when my descendants aren't going to have, especially my small grandchildren, aren't going to have a good time, are going to have it so much worse. I just can't stand it.
Okay. By the way, so how are we doing here? It's 11:44. I'm thinking, by the way, that in the future, when we're doing these live rooms on Zoom, that we should probably make them shorter than we typically do, because first of all, that it'll attract more people to listen if it's a shorter format. And I don't know, we'll have to see how it goes, because as we actually open this up to more people, we might actually have to limit, I guess, the people that get to ask questions. We have really lots and lots of people. And then what we can do is filter, do questions in chat, things like that, then select the right ones.
One thing that's worked really well on the MedTech Forum has been to have a 1 hour, formal session where you talk about the papers and you have a short Q&A, and then to have a foyer time period afterwards where it's more of a interactive conversation. And that achieves both of those objectives of having the shorter formalized business and then an informal roundtable where people can really discuss these things afterwards.
Yeah, I agree. And in a sense, that's what we have done. That's the general format we have. Very often there's a subject that I am covering or a guest that I'm interviewing, and that usually happens within an hour or so. And then we open it up for audience discussion, very often with the guest if they're here. And so, yeah, we kind of have that. And if we formalize that a little bit to keep the official initial room at 1 hour, and then if we post a replay, we could, post the 1 hour replay. Because I think if you post something longer than that, you're going to just scare. I mean, if it's more than 10 minutes, you'd probably scare off, 80% of the people. But we can figure that out. Also, they have Zoom has some like AI clip capability where it picks clips, things like that. So maybe we'll try some of those kinds of things. But however, I think we're going to try next week on this new software we were talking about, to try to to see if we can control the streams more, about where stream it to a reserved or a pre-scheduled YouTube thing. Also, the YouTube thing really seems to be running slow from my point of view. I don't know, maybe it's just me. So it may not.
I see a lag, and it's funny because it will join live and it seems live, but then over time it's like, oh, that's what I was doing that like 2 minutes ago, or I don't know.
Yeah, let me see what it says here. When I keep speeding it up.
Yeah.
I got to go back. I don't know. Oh, I lost it.
But I have it on mute, so I don't, because I don't want it to interfere with this, and so I don't know when or how it's doing that.
Here we go. I'm back to the stream.
Yeah, the time base drifts a little bit on YouTube, and you have to go to faster than real play to catch up again.
Well, it's looking at me looking up, so that means I'll look down, see how long it takes for me to look down. I don't know. It's a big lag, whatever it is.
Yeah.
It's a long lag. Okay. It's very distracting to look at, actually. So let's cover it up with Club Deck again. There we go. And on Club Deck, we have 18 there, and some are also here, some of them. Again, anyone on Club Deck has a question before we close down, You're welcome to join on Zoom by clicking on the link at the top of the room. That will take you to the Zoom room where we have a bunch of people and we can have conversations and things like that. So you're welcome to do that. Good. So next week will be this discussion of this new paper, which is coming out on the 24th. I believe it's the 24th. So Tuesday. And this will, you should, I'm sure I will post it on Twitter when it comes out. But this is going to be yet another warning from a group of scientists saying we, and includes other scientists, are not taking climate change, the dangers of climate change seriously enough. And that there's some fundamental failure, just like we were talking about, like the space shuttle, people not recognizing what's happening to the car industry, on and on, with all the signs, all the data you need, with probabilities that are way in excess of anything you would ever allow your child to, like, let's say you could have your child cross the street blindfolded and there weren't that many cars. So there's only a 20% chance that the child would be hit by a car crossing the street blindfolded. Would you allow your child to cross the street blindfolded in such a situation? What if it was only 10%? You would never do any of these things. It's insane to even consider it, right? You would never expose your children to that kind of risk. Yet the risk that they are facing because of climate change is much, much higher than that. I would argue it's 80, 90%. I mean, maybe an individual child, hard to say, depending where they live, maybe not that high. But, even 50% is crazily high. It's not even 50 times higher. It's 500 times higher than the risk that you would ever expose your child to. And, it's just, it's because of humans' failure, the inability to look at future problems that are distant in time, that aren't caused by an enemy, that don't have historical precedence you don't feel that they're going to personally affect you. You don't understand how they would personally affect you, since it's complicated with, vapor pressure deficit and ppms and all this kind of stuff. Doesn't make any sense to you. That's not, a lion biting your head off. You get that. That's scary. You can understand that. But this other stuff, too hard to understand. And it's also not visible and immediate. So it just doesn't have the things that we normally respond to threats. We want threats to be visible, immediate, have historical precedent, simple causality, direct personal consequences, and we want them to be caused by an enemy for us to react. And climate change, although it's starting to have some of those, it's starting to be visible, starting to be immediate, starting a little bit. It's just not something that humans are designed to react to. And they're not. Yet, if you think about it, if you actually use rational thinking, which is, again, not something that we typically do. It's not, not collectively. Yeah. Individual humans can be rational and think about things and whatever. But as a group, I kind of say that, individual humans are fairly intelligent, but the more people you get, the closer we get to being algae, sort of eating our way at a petri dish to the edge of the dish. And someone looks up and says, "Hey, I see the edge of the dish." And everyone else says, "Shut up, just keep eating," and you're just working your way out to the edge of the disc. And that's about as intelligent. It sounds like a joke, but I think it's fairly accurate. When it comes to climate change and us collectively, not individually, because everybody here is engaged on the subject, we're working on it in different ways and whatever, but we're a very small percentage of the population. And if you really look at the entire population, no interest in, there might be some concern. You read some article, you're concerned. Not voting on it, of course, because you're much more concerned about people using pronouns or whatever it might be. It's like, there's a lot of things that get you upset because they seem more urgent and personal at the time. But it's just not working. And, we will have to face reality, and the more climate gets real, and next year will be a test of this to see. Next year will be crazy compared to previous years. It's going to be 1.5 or more, actually maybe 1.7 degrees of warming, versus the only other year that we had a whole year was 1.2, 1.3 of warming. And that means we're going to have more of all. I mean, we're having it. It's already happening. We're already at that warming level right now. We're at 1.8, 1.9 right now. And we're seeing crazy floods all over the place. It's kind of you just look on Twitter, and today it's Rome, and yesterday it was somewhere else, and you just see the cars floating down the street as sort of a normal. I don't know. I didn't used to see cars floating down the street very often on the news. And we'll see more and more crazy fires and floods and droughts and crazy heat waves. There's heat waves in the wintertime in the southern hemisphere. Well, now it's changing, but it's like the warmest. They're having heat waves when it's not the right time of year to have a heat wave. And that's also true in Europe and things like that. So we're going to see more and more and more of these crazy signs of things happening. And we'll see if it does much to change the trajectory we're on. Because right now, the UK is backing off of its net zero commitments, for example, because they want to keep promoting fossil fuels. We're promoting, the good news is that renewables are growing like crazy. That sounds really good, except the problem is fossil fuels aren't going down. And it doesn't matter how fast or how much renewable energy we have. That will not stop climate change. We could have 10 times more renewable energy today. Actually, that would probably hurt climate change because of the fossil fuels go into making that renewable energy. But even putting that aside and saying that all that was carbon neutral somehow.
Have to be way. That's just the way that we're making it right now because it's the cheapest way.
Yeah,
Like,
but in the future, I'm saying, let's assume it's all carbon neutral for some reason. It still wouldn't change climate change at all if we don't also lower the fossil fuel emissions. That's the thing causing climate change. It's not the solar power causing climate change. It's the fossil fuels. And so far we've been growing renewables, and they have been taking up what maybe would have been increased fossil fuel use. So you could argue it's not as bad as it could have been, but that's not really going to make people feel good when climate change shit is hitting the fan and say, well, you know what? Yes, it's horrible out right now. And, then hundreds of millions of people are dying, but you know what? It could even be worse. So take comfort in that. What? I don't know if that argument is going to hold very well in the future. So that's why, and by the way, it leads to a simple conclusion that rather than focusing on promoting renewables, we should be focusing on phasing out fossil fuels. If you focus on phasing out fossil fuels, you will be promoting renewables. That will happen. But unfortunately, the reverse doesn't happen as we've so far, that fossil fuels have not dropped as we've promoted renewables. It will, by the way, eventually happen because renewables are so much cheaper than fossil fuels that even with all of the political corruption and everything, they'll eventually win and start reducing fossil fuel emissions, but not fast enough to protect society and civilization. So we actually have to step in and set policies to do that. So with that,
Well,
that's sort of yeah, go ahead, Eli.
The important things, like even when we completely stop emitting carbon from fossil fuels, right? There's still what's in the atmosphere. And as we discussed, the ability of plant growth to take up the excess is probably being significantly overestimated. So whatever's in the atmosphere is going to stay in the atmosphere for a long time and continue to drive excess heat being trapped. And so we need to do two things. We need to accelerate the rate at which carbon dioxide comes out of the atmosphere by carbon dioxide removal or ocean carbon dioxide removal, direct air capture. There are other methods, but also that best case that will take decades to get us back to pre-industrial levels. Most people don't even talk about going back to pre-industrial levels, but that's what we have to do if we want an energy balance that's consistent with a healthy ecology. But in the meantime, there's that excess heat being trapped that's continuing to drive all of these amplifying feedbacks. And so we need to really get serious about understanding all of the different options in terms of sunlight reflection management. In other words, not trapping, preventing sunlight from making it to the earth, or not trapping it or reflecting more of it back out into space, to restore the energy balance that is consistent with a healthy ecology, a healthy climate, and a healthy human civilization.
So, yep, agreed to that. Sunlight reflection methods, by the way, keeping it simple so the public will understand what it means.
Eventually.
Yeah. Well, I've been really trying to push it. It's like accurate. It actually describes what we're talking about, and it's understandable. So solar radiation management is descriptive, but is only really understandable by the scientific community, not by the general public. And it also
Well,
includes the word radiation, which
radiation is bad. Sunlight
Right.
is good. Reflecting. Oh yeah, I get that. Like that. Yeah. It's much simpler, cleaner, light.
and solar,
breezy.
so why not sunlight? That's really what you're doing.
Yep.
And as I say, it sounds like something you'd like to do on a sunny Sunday afternoon, at the beach. I need some sunlight reflection method so I can stay cool here on my blanket on
It's
the
a
sand.
parasol.
I need
It's
a
just a
parasol.
parasol. That's it.
That's
Yeah.
right.
Yeah.
Which is one of the methods, by the way.
Here we
A
go.
big fucking parasol. But yeah.
Right.
How big is that parasol, Eli? 400 square kilometers or something? What is it?
If you think of the Earth projected onto a two-dimensional disk, 1% roughly of that disk would do it.
Yeah, but how many square miles or square kilometers is that? I thought I heard you say it before.
Mean at L2 or we're talking about?
But at the top of my head at L1, I could calculate that. It would
No,
take
it's
a
okay.
minute.
All right. It's big. Let's talk about that. It's really big. Yeah, it's really big. To give you an idea, by the way, of we have to reflect about 2% of the sun's rays to cool the earth sufficiently to counter global warming, roughly speaking. The entire United States with Alaska and Hawaii is less than 2% of the surface area of the globe. Now, that's the surface area of the globe. We're not talking about the disk facing the sun. So that would be about pi less, is I think a third.
No, a quarter.
A quarter. So
pi
it's 4 times
versus
that. So it's 7-ish%, I guess. When facing the sun, it's 7%, but yeah. But it still doesn't matter. The earth rotates. So if you were going to put mirrors to reflect the sun and you needed, quote, 2%. By the way, I'd never understood this about mirrors. If anybody knows that mirrors is the project that promotes mirrors to cool the earth. So there's 4 basic ways. There's probably and some in between, but to cool the earth using sunlight reflection methods, the 4 basic sunlight reflection methods are: 1, put light colored or mirror something light on the ground to reflect the sun off, when it hits the ground to reflect it back. It mirrors. That's what mirrors, MEERS.org, maybe, is that they promote that. The other one is to brighten clouds and increase the number of clouds, marine cloud brightening. And that if you have more clouds, the clouds are light color, they reflect the sun away. So that would help. The third way is put particles in the stratosphere like sulfur. We currently put it in the lower atmosphere, which causes lots of pollution and it doesn't last very long there. It only lasts a week, but put in the stratosphere, it lasts a year. And therefore, you don't need nearly as much pollution to reflect the sun away. And that's what happened with a large volcano. It cools the earth when it puts a lot of sulfur particles in the stratosphere. So that's the third way. And then the fourth way is to put a sunshade, a parasol, between the sun and the earth at what's called the L1 Lagrange point, which is the point where the gravity of the sun cancels the gravity of the earth. It's much closer to the earth, because the earth is tiny, tiny, tiny compared to the sun. So it's very close to the earth, far from the sun, but just enough where it cancels the gravity. So the spacecraft won't be pulled towards the sun or pulled towards the earth. And it can always, just with a little push, always stay between the exactly in the same place between the sun and the earth. So if you make a big mylar disk that's 400 square kilometers or something like that, maybe on that order of magnitude,
it's actually 2 million square kilometers to cancel out about 1.5%.
Yeah, so what's a few million
of-
kilometers between friends, Okay, you said two?
Does that
Two-
need to be all in one big blankie?
No,
Or can
no,
it be
but-
in, chopped up and,
It could be chopped up.
okay,
And
so
in fact, some people
Yeah.
are proposing to, rather than build flat sheets, which you then need a structure to hold it out, just make balloons and tie the balloons together, but big balloons made out of mylar. And it's very easy to deploy because they just need a few molecules of atmosphere from the earth in them. They're just tiny, to suck out, quote, all the air and compress them, right, into a tiny spot. As soon as you put them in space, there is zero pressure in space. So whatever few molecules of air are still left in them, even though you thought there was no air left and it's all compressed, all of a sudden it will expand into a huge balloon because of the zero air pressure in space. And then tie them together somehow. You don't need to have you don't need a metal structure anymore. And you just think of it as the movie Up, with the house floating away with all the balloons. But now just imagine something that's 200, what is it? 2 million square kilometers of
so
a
basically,
disc.
so basically, after every marathon, we collect the little mylar blankets that everyone has, and then we have some sort of duct tape sewing bee or
There
whatever,
you go.
and then we put it up, and we're
There
good.
you go. And then,
Yeah. Reduce, reuse, recycle, reflect is, yeah,
another R.
there you go. Yeah.
Reflect.
The-
So
honestly, you wouldn't get as much benefit out of it, but simply like laying out the reflective mylar on a dark roof will probably like keep the house a bit cooler
mhm.
and be somewhat, again, not as effective as Lagrange point one, but per dollar, probably more effective in the short term.
Yeah.
So,
That's
that
true, by
was
the way.
put-
Just painting your roof white is a good thing to do.
okay.
But
So-
you got to
so-
remember, even no matter how many roofs we paint white, I mean, it will be helpful, but will not cool the earth, the 2-degree warming of the earth. I mean, it's not gonna do that.
Gotcha. Okay.
So that's the 4 main ways, and I bet there's a few in between ways there, but everything from putting mirrors on the ground to putting sunshades in space and is sort of the ways to artificially cool the earth. A very important aspect of sunlight reflection methods versus everything else we can do, including lowering our emissions and sucking CO2 out of the atmosphere, is it provides cooling immediately. As soon as there's a large volcano, the earth is cool for the next 2 years. All right, it happens right away. And everything else we would do, such as lowering our emissions, I mean, the impact of that you feel 30 years later by having slightly less warming than you do now. And again, it doesn't cool the earth. Reducing your emissions doesn't cool the earth. It just stops the earth from getting as warm as it might otherwise get.
No, wait a minute. Isn't the caveat that the volcano needs to be on land and not underwater?
The volcano needs to put up, by the way, it has to be a really big volcano because most volcanoes put up their sulfur into the lower atmosphere. You know, maybe where planes fly or something like that. And that really screws up planes, by the way. Plane, all that you're basically flying an engine through a sandblaster. And then that destroys, there's really harrowing examples of planes accidentally flying through volcanic ash and all of a sudden losing all four engines, like on a 747 or something, and almost crashing, but not. But that falls out of the atmosphere very quickly after a few weeks and might have local cooling happening, but not global cooling. So you need a Mount Pinatubo. You know, it happens a few times a century. It's not something that happens normally. It's so strong that it throws up it in the atmosphere. Now, the Hunga Tonga volcano did throw up a lot of ash or sulfur, but also threw up a lot of water vapor because it was underwater. And it was the first time we've ever seen it, so they don't really even know much about it. Some research studies said it ended up heating the Earth, and some said it cooled the Earth. I mean, taking both factors into account, some said the cooling was stronger than the heating, and some said the heating was. But the bottom line is, no matter what it was, it's not very strong now because it's been a couple of years now, and so the warming, where some people are trying to say, oh, this crazy warming, the 1.5, that's all Hunga Tonga. But as Jim Hansen pointed out, that's not the case. It doesn't appear to be the case, I should say. There's a lot of uncertainty in it. Again, the first time we've ever seen it. Biggest explosion ever recorded on Earth. There were bigger ones in the past, but we weren't recording way back when. Like, I don't know, Krakatoa might have been bigger. But anyway, so we've learned, we know a lot, we know what's going on, and we need to act, and we're not. And this idea that we can know all we know and not be concerned, not declaring an emergency. And again, this paper coming out on Tuesday, it's all going to talk about all of that. So keep an eye out for that, and we'll talk about it next Sunday. But I think with that, we'll sort of wrap it up.
Just wanted to make the point home that sunlight reflection methods are the one thing that we can do to slow the rate that we are advancing towards tipping elements. And there's a lot of uncertainty about tipping elements, but we can have a lot of certainty about exactly how much sunlight we are reflecting. And this is the only insurance policy we can buy, and we're not buying it fast enough. So we gotta double down on balancing the heat and energy budget of our planet while we still can.
Well, it's worse than that, because it's not like we don't know about this. We do know about it, and many people, and I mean people in the climate action community, are violently opposed to doing sunlight reflection methods. They think there might be negative side effects to doing it. And they think there might be social justice issues by doing it. In other words, it might help one country more than another country or something like that. And that is all true. But that's not really the question. The question is, what are the side effects or the negative impacts and the social justice issues of doing it compared to not doing it? And when you look at that, I don't know how you can come to the conclusion that it's anything but not a little more by not doing it. It's 10, 100, 1,000 times more by not doing it. The whole point of doing it is to reduce the geoengineering, as Jim Hansen put it. The point of sunlight reflection methods and carbon dioxide removal is to reduce the geoengineering that we're doing to the planet. It's not like we have a status quo as a baseline. The baseline is a world where we've increased CO2 by 50% and greenhouse gas forcing by 100% in a very short period of time. And now we're going to find out what that means. And we probably don't want to find out what that means. So it's not just that we're not doing it. People are actively against doing it. And I tell everybody that when I talk about this, I said, look, this is something that everybody is against, and we're going to do it. And the reason we're going to do it, we're going to wait maybe a little too long, but people will be really unhappy when the shit is hitting the fan. And things are just getting bad really fast. And it hasn't happened yet. The stuff we're seeing is just a taste of the future. And when it's really getting bad, the only choice that will change things quickly is sunlight reflection methods, as Eli is pointing out. So that will be the only tool in the toolbox that could have a quick effect. And as we know, politicians want things that happen quickly. And that's going to be the only choice. Now, it doesn't mean that's the only thing to do. We still have to reduce our emissions and all that stuff. But so we're going to end up doing it. And I think we're going to end up doing it much sooner than people think because of that. Because things will get bad pretty fast. And that will be the only, the only tool in the toolbox that will react quickly to changes. And people want that. People want take action now and then something happens. They don't want to take action now and something happens in 30 years. They just don't think that way. They don't care. They don't care about 30 years from now. We know that. We're already looking at what's happening now, right? That's why there's so much net zero in 30 years. Hey, great. We don't have to do anything now. We'll just wait for 30 years and we'll go from there. And maybe, let's see if I can say this. I'm going to see if I can find this here. It's very funny if you haven't seen it. Yeah. So see if I can share this, do a little more screen sharing. We'll end on this here, share screen. For those you can't see, it's a picture of a guy holding a glass of beer. A man announces he will quit drinking by 2050. A Sydney man has set an ambitious target to phase out his alcohol consumption within the next 29 years as part of an impressive plan to improve his health. The program will see Greg Taylor, age 73, continue to drink as normal for the foreseeable future before reducing his consumption in 2049 when he turns 101. He has assured his friends it will not affect his drinking plans in the short or medium term. Taylor said it was important not to rush the switch to non-alcoholic beverages. Quote, "It's not realistic to transition to zero alcohol overnight. This requires a steady, phased approach where nothing changes for at least 2 decades," unquote, he said, adding that he may need to make additional investments in beer consumption in the short term to make sure no night out is worse off. Taylor will also be able to bring forward drinking credits earned from the days he hasn't drunk over the past 40 years, meaning the actual end date for consumption may actually be 2060. To assist with the transition, Taylor has bought a second beer fridge, which he described as capture and storage method. Anyway, so that's go out on a little light note for that. I'll post that here in all the various thingamajiggies here. So I should put this on.
That was hilarious. And yeah, if you wouldn't mind, Dan, posting, I put this in the notes along with all the other things that you've referred to in that bit.ly. If you just post the bit.ly, that will.
The bit.ly thing? What was that? I'm sorry, I'm not
so
sure.
I sent you a message on
Oh.
Zoom that says about this bit.ly/climate
Oh, okay.
chat notes. If you can put that on YouTube,
I
it's
see.
the same Google thing I have, and all of the things that have been on screen or yeah, that we've discussed are in that.
Yeah, I got to get back to the stream. There's the stream. Okay.
Yeah, because you can post links, but when I'm posting it or Lightning Rod was trying to, we can't post links to anything. Only you can
Okay.
post links.
Okay. Yeah, I
So-
think I set that for safety
Which-
reasons.
Yeah, yeah, it makes sense. It's just when you're trying to send it, it doesn't.
So here's
The
the
mere
doc,
mortals
here's the
over here.
bit.ly thing. Okay, I posted that.
Yeah. So that's like the Google, that's the same as the Google Docs, whatever it.
Well, it is Google Docs. I think it showed up as
Yeah,
Google Docs.
I just made it. Yeah.
Oh, I see. When I type, since I'm screen sharing, when I do that, you can see all that stuff. Okay.
Yeah.
Anyway, all right. So we're all back, and thanks everyone. So let's see. Let's summarize a few things going on. I'm on a podcast tomorrow with Adam McKay, the director of Don't Look Up. So that should be interesting. And I don't think it'll be posted tomorrow, but I'll let you know next time where you can see it. There's a paper coming out on Tuesday that's embargoed, which means I can't talk about it. But will be coming out, and it involves somebody that we've interviewed here on this program. And if we're lucky, we'll get them back to talk about this paper next week. And it's a warning from climate scientists to say we're not taking climate change seriously enough, and that's very true. And so that will be next week's. And next week we're going to try some new technology, because I think, we're sort of where we were last week in terms of being able to be simultaneously on Zoom and Club Deck. And we are streaming to YouTube somehow, but we weren't able to post that link ahead of time, and there's a delay, and I don't know how good it is. I'll watch it afterwards. So we might be trying something new next week, but we'll all be, we'll put whatever it is on on Clubhouse. We'll put those links. We'll put them on Twitter. So if you're not following me, you should, at Dan Miller 999. At Dan Miller 999 is my Twitter or X handle. And we'll put it there. I'll probably put it on LinkedIn also. And we'll go from there. We'll get this thing popping. And once we get the technology working, then we'll focus on expanding our reach. But I think until we get the technology kind of down pat, it doesn't make sense to promote this too much. I think there probably were a few people that maybe followed the Twitter link to the YouTube channel and it didn't work. So that's probably frustrating. We don't want to frustrate too many people. So we'll get that going. And JP, appreciated your help so far on that. So looking forward to working out something else for next week. So thanks everybody. It's 2.5 hours, so that's pretty long. And it's nice to actually see people here.
Will the Zoom link continue to be this Zoom link?
No, but I think it's going to be a new Zoom link each time.
I think they tend to be dynamically generated. So
right, I do have a
same with
fixed
YouTube.
one, but that's my personal one. I don't want to use that for this.
Well, you can schedule. You can schedule. I can send you something about that.
No, I am.
You can
This was
schedule
scheduled.
repeated.
This one was scheduled. So I could
You
have
can
posted
schedule
it
repeated.
on ahead of time, but I didn't do that because, again, I wanted to see how this thing is working here before I start to do that. And yeah. And one thing we didn't have, and I guess we couldn't really have since it wasn't public yet, is we didn't have like the trolls coming around, so that was good. The YouTube thing was, unfortunately, was private, so only certain people could see it. So that's limited. But we'll work on all of that. So thanks everybody. We'll see you next time. I'm not going to play music here. We're gonna have to get some royalty-free music. somehow.
There's a lot of public domain stuff.
Right,
that
but
you
if
can
anything
find
that's
on-
climate-oriented public domain music, please email it to me, Dan, at climatechatclub@gmail.com. climatechatclub@gmail.com if you have suggestions for royalty-free climate-oriented music, or just some cool music you think would sound good on the channel for intros and outros and things like that.
Maybe that's one thing you can ask Adam McKay.
Aha. Oh, you can, yeah, can we use your Don't Look? Well, I see it's Bev, right? The Saturday group is using the Don't Look Up music for on Clubhouse, right?
Yeah,
I think.
but we don't have actual permission. I tried to reach out to the composer, but he hasn't replied. Well, I don't know if his agent received the message or read it.
Yeah. So, but I think on Clubhouse they have a blanket license or something that they pay for this. I don't even know. But YouTube does it too. But the problem is if the composer, they get a notice that your music's being used and they can turn it off and stuff like that. And they can block your video and things like that. So speaking of that, there's a great movie, The Big Broadcast of 1938. It's an old movie with Bob Hope in it. And he sings Thanks for the Memories, which is like his theme song. And it's a really good song. And I was watching it the other day with my friends, and the movie's playing, and then they get to the song, and then the whole thing goes silent because basically someone is, posting this on YouTube and knows if they play that music, it'll be tagged and the video would be removed. So they take the best part of the movie, they silence it because of YouTube algorithm. So we're going to try to avoid that. So on that note, thanks everyone. We'll see you next time. It's like, I hope you like my little background I created for this here, and
Yep, it's looking good.
very good. So see you next week, and keep an eye out on Twitter for on Tuesday for this paper being posted, and suggestions and everything. climatechecklub@gmail.com.